Hello everyone. Welcome to the second lecture of the course in commutative algebra. So earlier we have talked about rings, ideals, and basic definitions and terminologies about ideals, etc., prime ideals, maximum ideals, etc. Since I have remarked earlier that ideals will be one of the most important things which we want to study. So the whole study of commutative algebra is based on the study of ideals of commutative rings and more generally things which works like ideals, like modules, etc., which will be introduced later on. So in today's lecture, we are going to discuss some more properties of ideals, and we'll do some operations on ideals. We will in fact give some structures of ideals in some cases. So without further delay, let us begin with that. So in the last lecture, I have defined prime ideal, maximal ideal, and I also showed some of the properties. In this lecture, I want to begin with some examples of prime ideals and maximal ideals. So as a prototype, take the ring Z. So if you take the ring Z, you can verify that the set of all prime ideals of Z is generated by the elements P, where P is either 0 or a prime integer. So this is easy to check that spec Z contains all these elements only. Similarly, you can also check that maximal spectrum of Z consists of only non-zero primes. This is not a discrete case. If you look into a PID, so here is an exercise that in a PID. So what is a PID? PID in its full form called principal ideal domain. This is an integral domain where every ideal is principal. That is, every ideal is generated by a single element only. So an integral domain where every ideal I of A are of the form Ax, or sometimes that will be denoted by X, and this thing means Rx, thus the R is in A. So this contains all the multiples of all the A multiples of X. Remember, A is a commutative ring with unity throughout, unless I am mentioning it otherwise. Okay, so you can check that in a PID, every non-zero prime ideal is a maximal ideal. That is, spec Z, sorry, not Z, spec A minus this zero ideal is actually your M spec A. So remember, in an integral domain, zero ideal is always a prime ideal. So spec A will always contain the zero ideal, but if you remove that, it will be the maximal spectrum. Okay, this is not very difficult to prove. If in fact I am giving you some idea, like suppose P is a non-zero prime ideal, and you want to show that it is a maximal ideal. So suppose P is contained in some maximal ideal M. P is proper. So by the result we did in the last lecture, we can say that P is contained in some maximal ideal M, but M is generated by something else, some Y, let's say. So now your ideal generated by X is contained in ideal generated by Y. So you can write X as sum R times Y, where R is coming from A. But then either R or Y must be inside the ideal generated by X. So suppose, if R is in the ideal generated by X, then R is some Sx. R is of the form Sx. So that means Sy will be 1 if you cancel out X, because X is non-zero. So that means your Y is a unit and the ideal generated by Y is the whole ring. So it cannot be maximal. Therefore, R cannot be inside X. Therefore, your y must be inside x, but then you can again check that this r will be a unit and the ideal generated by y is the same as the ideal generated by x, and therefore the maximality will follow. Okay. So this is the case of a PID. In fact, another exercise says that in a UFD A, every in a UFD A, every non-zero irreducible element generates prime idea of A. Okay, so this is the scenario for PID and UFD. So what is an UFD? UFD is an integral domain where every non-zero non-unit element can be uniquely factorized up to reordering into irreducibles. Okay, so I am assuming that people who are seeing these lectures are accustomed to all these things. Okay, so those were the cases for UFDs and PIDs, and that means you have now plenty of examples for prime ideals and maximal ideals. Okay, however, I have not talked about polynomial rings yet, that I will be doing shortly, and then you will have even more examples in your hand, and you will see eventually that we will be essentially interested about polynomial rings for a large amount of time. Besides, we will do things on general rings, but okay, all these things will come later on. Okay. Okay, so now I want to talk about rings which has only one maximal ideal. So those kind of rings are called local rings. Again, one importance of this kind of local rings is that this will be very much useful in the study of commutative algebra a little bit later, because local rings you will see later on from some topological perspective. Local rings will correspond to rings which are determining some neighborhoods of a given point. Now, all these things I am saying it vaguely, but this can all be done rigorously, and we will do that later on. Okay, so what is a local ring? A ring A with only one maximal ideal is called a local ring. So while denoting local ring, we will be denoting them by this symbol AMK, where K is the residue field. So K is the quotient of A by this maximal ideal, hence it is a field, and this will be called the residue field. Okay, so how to determine local rings? First of all, observe that observation that if AM, I can sometimes write this also. AM is a local ring, then A minus AM is essentially A star. And this observation will lead us to some characterization of local rings. I mean, how to determine whether some ring is local or not. This will be a crucial observation in that regard. So in that line, let me write down a proposition for a ring A. The following are equivalent. Number one, A is a local ring. Number two, there exists an ideal of A such that A is a proper ideal such that A minus I is contained in A star. That is, every element of the complement of that ideal is a unit. And number three, A minus A star forms an ideal. And if any of 2 or 3 holds, then M is actually A minus A star is the unique maximal ideal of A. This is again self-explanatory. So I am just giving the outline of the proof. So if you take a local ring, suppose M is the maximal ideal, then by that observation, M is the proper ideal. For the second condition, M is the proper ideal I, for which the complement contains all units. And if 2 is getting satisfied, then for 3, observe that first of all, we know that there exists an ideal I such that the complement contains all units. So I, since it is a proper ideal, this is the subset of A minus A star. So you have this. Your I is a subset of A minus A star. This is what you already know. And now if you have an element of A minus A star, you want to show that this belongs to I, but whatever this belongs to some maximal ideal M, right? So what you want to show is that if you take an element which is not a unit, then it is contained in the ideal I, then you will be able to show that this happens. Okay, so if it does not belong to I, then that means it's a unit, right? This is a contradiction. So it has to belong to I. And thus you are getting that I equals to A minus A star, and by the hypothesis I was an ideal, so A minus A star forms an ideal. So we need to prove only 3 implies 1. So when A minus A star forms an ideal, we want to show that A is a local ring. So first of all, see that any non-unit element is contained in A minus A star, and anything more than, if you take A minus A star and if you attach any more element there, then it will be the proper ideal, then it will be the whole ring, and therefore A minus A star, if it forms an ideal, then it is a maximal ideal. And now I want to show that this is the unique maximal ideal. So take any other maximal ideal, or take any maximal ideal M, take an element X, it is a non-unit, so it is in A minus A star, which is a maximal ideal, therefore M will be equal to A minus A star, and the ring A is a local ring thereof. So what we get is the following characterization of local rings. Okay, maybe I can add one more thing, that so suppose another proposition is that, suppose A is a ring and M is a maximal ideal of A, such that every element of the set 1 plus M is a unit of A, then A is a local ring. So what you essentially want to show is that M is the only maximal ideal. So take any other element. So if you take any other element, let's say X, not from M, then okay, so I want to prove that A is a local ring. So I am assuming that there is one more maximal ideal. I will eventually get a contradiction. So if there is one more maximal ideal, let's say N, so take some X in N which is not in M, I will get one such thing. Otherwise, if N minus M is empty, then N will be contained inside M, and by maximality both will be the same. So you will get some X from N minus M, and you take the ideal generated by M and X. This will be the whole ring because M is maximal ideal, and thus you are getting some element of this form M1 plus xt equals to 1, and then this xt which turns out to be 1 minus M1, this is a unit, but that will imply X is a unit. So X cannot be in the maximal ideal N. So it cannot have any other maximal ideal, and therefore is a local ring. So these two are some easy propositions to prove, but they are extremely important that you will see soon. Okay. Even there is a slightly, there are rings which are very much close to local rings, but not exactly. So they are called semi-local rings. A ring A with finitely many maximal ideal is called a semi-local ring. So this is called a semi-local ring. And again, we will see that the semi-local rings are also an important class of rings, because, okay, not all of semi-local rings. So we'll study some class of rings which will turn out to be semi-local, and those have some particular importance again. So that we will see eventually. Okay. So having said that, so today what more we are going to do is the following, that we are going to study some more properties of some nice ideals, like one I mentioned earlier called nilradical, Jacobson radical, this kind of things. And then we will be looking at things, looking at some results, namely the prime avoidance lemma and Chinese remainder theorem. So all these results have some importance both geometrically and algebraically, that we are not in a position to discuss it right now, but we are heading towards that. Okay, so let me start with nilradical. So proposition is the following. We have discussed that nilradical forms an ideal, and okay, so I am mentioning it again, is an ideal, and A mod nil A, if you look at this ring, then is a reduced ring. Now, what is a reduced ring? Reduced ring means a ring is called reduced if nilradical. Okay, so a ring A is called reduced if nilradical A is the zero ideal. So those kind of rings are called reduced rings, and by the virtue of this result, we will be calling this A mod nil A as A red. So another symbol is that this A mod nil A will be defined as A red. So A reduced. So if you reduce the ring A, that will always mean that you go quotient modulo nil radical of A. Okay. So one part of this result we have already discussed, that why nil radical is an ideal. So I am giving you some idea about that result, how to prove that. So if you take two elements x and y from the nil radical, first of all observe that 0 is an element, so it is never empty. And if you take x and y, suppose x to the power m is 0 and y to the power n is 0, then if you take x plus y whole to the power m plus n, then you expand it by binomial expansion, which holds for commutative rings, and you can see that x plus y to the power m plus n will turn out to be 0. Therefore x plus y is there. And if you have x to the power m is 0, and for any ring element a, ax whole to the power m is a to the power m x to the power m, that is also 0. So it is an ideal. And if you take a mod nil a, so if you take an element from a mod nil a and such that this element x bar or class of x or x, I am referring that, raised to the power some n is 0 in that quotient ring, that means x to the power n belongs to nil radical of a. That means x to the power n whole to the power m is 0 for some m, and that means x to the power mn is 0. Therefore x is in nil radical of a, and therefore the class of x is 0 in m or nil a. So it is a reduced ring. But more important result is that your nil radical of a is actually intersection of all the prime ideals of. So this is something which we are going to prove. One part of this result is clear, that if you take any element from nil radical of a, then some power of it is 0, and suppose x is that element, then x to the power n is 0, and that means x to the power n belongs to every prime ideal, and induction argument will show you that then x is inside every prime ideal. So this inclusion is clear to you. But for the reverse inclusion, what we will do is that you take an element outside nilradical of A. So that means what? That means x to the power n is never 0 for all n in natural number. So what we will see that we will find out a prime ideal which does not contain x, and thereby by contrapositive statement you will get that intersection P is a subset of nilradical of A. So you take this collection of all the proper ideals of A such that x to the power n does not belong to I for all n natural number. You see that the collection is non-empty because 0 ideal is there. And again use the argument we did for the existence of maximal ideal, the John's lemma kind of argument. You take a chain and you take the union clearly becomes an element of C, and hence every chain of elements in C has an upper bound in C, and therefore by John's lemma there exists a maximal element. So by John's lemma there exists a maximal element. I am calling that P. So now I want to show that P is a prime ideal. So for that, suppose AB belongs to P for some AB belongs to A and B both does not belong to P. We want to derive a contradiction from these. So A and B does not belong to P. That means P plus A and P plus B. These are ideals which strictly contain P. And P is a maximal element of C. That means these P plus A and P plus B cannot be in C. Therefore, some x to the power m belongs to P plus A and some x to the power n belongs to P plus B. So if you break it down, then it will be of the form P1 plus AR1, and x to the power n will be of the form P2 plus AR2, where this R1, R2 are elements of the ring, P1, P2 are elements of the prime ideal. P, elements of the ideal P. We have not shown that it is prime. We are going to prove that. Okay. Then x to the power m plus n, if you multiply, then it will be of this form. Plus A. Okay, so it will be B. I'm sorry. It will be B. And this belongs to P. But that's a contradiction because P cannot contain any power of x. And therefore, P has to be a prime ideal of A. But P is in C. Therefore, P does not contain x also. That means nilradical of A. Okay, that means x does not belong to nilradical of A implies x does not belong to the intersection of the prime ideals of A. And that completes the proof by taking the contrapositive argument. Okay, so what we could see is that the nilradical becomes the intersection of all the prime ideals of A. But remember, in the last class we did one result which says that the nilradical is contained in the set of all zero divisors, and thus we will prove some similar result for zero divisors also. Usually, what you can see by taking several examples of rings, that nilradical sometimes, in fact, most of the times it will differ from the set of all zero divisors. But what you can show is that your zero divisor set is always a union of prime ideals. So another proposition is the following: the set of all zero divisors of A is a union of prime ideals of A. And the proof will again be a John's lemma argument. The proof is the following. So I am opening the statement in the left-hand side page. The proof is the following. you take C to be the collection of all proper ideals such that I is contained in the set of all zero divisors. That means you take set of all proper ideals which consists of zero divisors only. And if you take that, then you see the C is non-empty because the zero ideal is there. And thus again we will use subjohns lemma kind of argument. Therefore, if you take again a chain and you take their union, it is an ideal, like we did in the case of in the case of existence of maximal ideals. And for that thing, you see each of the ideals consists of zero divisors only, and therefore the union will be inside zero divisor set. So each chain has an upper bound in C, and therefore by John's lemma, C has a maximal element some M say. So now what I'm going to show is that this M is a prime ideal again. Now if not, then again you have this suppose AB belongs to M with A and B does not belong to M. But then this M plus A and M plus B, these are not contained in the zero divisor set, and therefore you can find X and Y from there such that X and Y are not zero divisors of A. But then if you take their multiple, then XY belongs to M. This is the similar argument that we did before. You take the you write down the elements using elements of M and elements of the ideal generated by A, and you take similarly for B, and you take the product and you will get this thing. So you can say that this XY belongs to M, but that means XY, the product XY is a zero divisor. But XY is a zero divisor means what? That there exists some non-zero z such that X times XYZ is zero. But now you take this element YZ. If YZ is zero, that means Y is a zero divisor, which cannot be the case. If that is non-zero, then X is a zero divisor. That cannot hold either. And therefore, what we get is that this is again an absurdity, and that will imply this is a contradiction, and that will imply M is a prime ideal of A. So what we can obtain is that every so this C has a maximal element, and if you take any maximal element of C, then that is a prime. This same argument works for every maximal element of C. So now if you take any zero divisor, you take the ideal generated by that. So suppose X is a zero divisor, you take the ideal generated by that, then this belongs to C. Clearly every element of X, every element of the ideal generated by X is a zero divisor, and hence this is contained in some maximal element of C. So X is contained in some M prime, where M prime is a maximal element of C. But all the maximal elements are primes, and what you have shown is that the zero divisor set is contained in the union of maximal elements. So what you obtain is that therefore zero divisors of A is contained in the union of M, where M is a maximal element of C. So that means your zero divisor set is contained in union of some prime ideals, right? But M is a maximal element of C, so each of the elements of M are zero divisors, and therefore this union is again contained in the zero divisor set, and that completes the proof that you get zero divisor set as a union of maximal elements of C, and all of them are prime. Therefore, the set of all zero divisors is a union of prime ideals of A. So this is something what you can achieve from there. Okay. So we have done some results on local rings, and we have done some results on we have seen something for this nilradical also. Okay, good. So now I am going to define something called Jacobson radical. So what is Jacobson radical? Jacobson radical is the intersection of maximal ideals. So like we did for prime ideals, the intersection of prime ideals was called nilradicals. This motivates us to refine the intersection of maximal ideals also. And therefore, what we are going to do is that we are going to give a definition in a ring A, the intersection of maximal ideals is called the Jacobson radical. Okay, and I will denote it by J of A. So this will be the notation. So what is J of A? This is defined as intersection of elements of maximal spectrum of A. Okay. So one result I would like to mention is that it's very trivial to check that if you take intersection of any family of ideals, then it is again an ideal, and therefore Jacobson radical is an ideal of A clearly. Okay, so this is an ideal of A. JA is an ideal. Okay, and okay, one more clarification I wanted to make is that for now, this symbol spec A and M spec A just denote a set. This does not, as of now, this does not have any topological structure or something like that, but we will come to that later on. Okay, so this is the definition of Jacobson radical. Now, if you want to characterize Jacobson radicals, since it is already an intersection of maximal ideals, that characterization is always there, but we want to get some characterization in terms of elements. So in terms of elements, we have the next proposition, which says that X is in Jacobson radical if and only if 1 minus xy is an unit of A for all y in A. Okay. So the proof, one part is very simple. If X belongs to Jacobson radical, that means X belongs to every maximal ideal. Now, suppose some 1 minus xy is not a unit, then 1 minus xy must be inside some maximal ideal, and 1 minus xy is inside some maximal ideal, and X is in that maximal ideal because X belongs to every maximal ideal. That means xy is in that maximal ideal. That means 1 resides in the maximal ideal, but that makes the maximal ideal to be the whole ring that we cannot afford, and therefore that is a contradiction, and therefore 1 minus xy is unit for every y in A. So this part is obvious. And for the reverse statement, so suppose your X is not in the Jacobson radical, then what happens? So we want to show that 1 minus xy cannot be a unit. So if your X is not in the Jacobson radical, then there exists some element of maximal spectrum where X does not belong, such that X does not belong to M. But then if you take this ideal, this is the whole ring, and therefore your 1 has an expression like this, where your A is a ring element and M1 is an element of that maximal ideal. But then 1 minus xa, which is M1, this belongs to M, and this is contained in the set of all non-units. So your hypothesis is not getting satisfied, and therefore 1 minus xa is not a unit. And by contrapositiveness again, you will see that therefore 1 minus xy is unit for all y in A implies X is in the Jacobson radical, and this completes the proof. Okay, so we have seen two characterizations of nilradical, namely intersection of all the prime ideals, and obviously in terms of the nilpotent elements, that was the basic definition. Similarly, we did the characterization for Jacobson radicals. Okay, so having said that, what I am planning to do is the following. So I am now going to define something called radical ideal or radical of an ideal. So we talked about this nil radical, And this is by as the name suggests that the radical ideal is something which is connected to nil radical, and this is exactly the case. So what is a radical of an ideal? So suppose A is a ring and I is an ideal of A, then we define by the square root of I the set of all x in A such that x to the power n belongs to I for some n in natural number. So this is the set of all elements of x which some power belongs to the ideal I. Okay, so this is called the radical of an ideal I, and an ideal I is called radical ideal if square root I equals to I. Although the definition looks simple, in the study of algebraic geometry, this radical ideals plays a great role, and that's why I am defining all these terms here, because eventually we will see that they have some roles to play. Okay, so now how is that connected to the nil radical is the following. First of all, observe that this I is subset of square root I for every ideal I. Okay, and also observe that, so observation is the following. So you have this ring A and you have the natural projection to A mod I. So you know that there was a correspondence theorem between ideals of A mod I and ideals of A. So you can see that if you take the nil radical of A mod I, and if you take the preimage of that, that is exactly this radical idea. So going modulo I, this radical of the ideal I is actually the nil radical of the ring A mod I, and therefore some properties will be there. So I am listing down the properties which I am not going to prove, but I will tell you some of them, how to prove them. So properties, these are easy to prove, these are just verifications. So first of all, I have already mentioned that I is a subset of your radical of I. See, radical of I is equal to the whole ring if and only if your I equal to the whole ring, and that's because radical of I, if it contains 1, then some power of 1 is again 1 is inside I, and if your I is the whole ring, then I is contained in the radical. So that is clear. Number 2, if you take radical of a radical, then it is the same thing. So radical I is a radical ideal. And why is that true? So first of all, radical I is contained in radical of I. And if you take x from radical of I, that means what? Some power of x is inside radical I, and then suppose x to the power m is in radical I, and then that means some x to the power m power some n is in I, but that means x to the power mn is in I. That means x belongs to radical of I. So this is also clear. Number 3, is that, so suppose P is a prime ideal and I is contained in the prime ideal P, then radical of I is also contained in the prime ideal of P. In particular, if you take radical of P is P. So radical of a prime ideal is the same prime ideal. That means prime ideals are radical ideals. So how is that true? If you take some x from square root I, radical I, then x power some n is inside I and hence in P. But again, an induction argument will show you that x is in P. So you are done in that way. Okay, so what I'm defining right now is what we call product of ideals, because I need that thing to give the next property. So suppose A is a ring and I, J are ideals of A, then define ij to be finite sum of elements of the form product of an element of I and element of j. This is a finite sum. Then you can easily check that this ij is an ideal of A, and this is called product of the ideals I and j. Okay, so we have already said that intersection of two ideals is an ideal, and therefore you can check this also holds. Ij is a subset of I intersection j. This is by definition because every element in the summand is in I and as well as is in j. You can also define product of, I mean, a family of ideals. So if you have a family of ideals I alpha is a family of ideals. I alpha is a family of ideals. Then product I alpha is the finite sum of, again, elements of the form x alpha 1, x alpha 2, x alpha k, where this x alpha I belong to I alpha I for some I. This is finite sum of product of finite elements of I alphas. And again, you can see that this turns out to be an ideal of A. Okay. And thus, in the virtue of that, you can now define what is some power of an ideal, some power of a prime ideal, etc. These things are there. Okay. Okay. So now I am adding a few more properties in our list of properties of radical of an ideal. So see that radical of ij is same as radical of I intersection j is same as radical I intersection radical j. Here I am giving you a simple exercise that show that ij not equals to I intersection j in general. So you have to find out examples for which product ideal is not same as the intersection of the ideals. The example is not difficult. So a hint is that you can find it in Z itself. So, okay. But what the property is saying you is that although they are not equal, this is just this containment is there, but they are not equal as ideals. But if you go to the radical level, then they are equal. So how is that true? So if you take some element, so first of all, okay, one more result I'm mentioning. I should have mentioned it earlier, but I forgot. So anyway, so suppose I is a subset of J, that implies radical I is a subset of radical J. Obviously, the previous properties showing you that the converse may not be true, because radical I intersection J will be subset of radical Ij for every I and J, but they are not equal in general, or they are not contained in one another in general. Okay, so first I am proving the fifth property. For that, if you take any element x in radical of I, then x power n is inside I for some n, and therefore x to the power n is inside j for that n, and thus x is in the radical of j. So that part is done. So using this, you see one implication of 4 is clear, that ij is a subset of I intersection j, and therefore this radical of ij is a subset of radical of I intersection j. That holds. But for the converse, if you take some x from radical I intersection j, then some x power n belongs to both I and j. But then x to the power 2n belongs to radical of ij. Ij. And thus x belongs to radical of ij. And for the other one, again see that this radical I intersection j is contained in radical I and radical j, therefore is in the intersection. Now if you take some x from radical I intersection radical j, then x power something is in I and x power some other index is in j. Suppose x power m is in I and x power n is in j, then x power m plus n is in both I and j, and therefore it is x is contained in the radical of I intersection j, and thus proving the fourth property. Okay, so we are done with that. Also we have this one, that radical of I power n is same as the radical of I for all positive integers n. That is again because first of all I power n is contained in I. So if you take the radical, one inclusion is clear. And if you take some x from radical of I, then x power some n is in I. You take the power n, then x power m power n, that is x power mn is in I power n. And that means this x power mn, that is x power n whole power n. But this x power mn is in I power n. That means x is in radical of I power n. So the other inclusion is also obvious. Okay. Also, I want to define what is called sum of ideals. So for ideals I, j of A, you define I plus j to be the set of all elements like this. You take a sum of elements of I and of j. And you can also define this for a larger class. This is finite sum of x alpha, where x alpha belongs to I alpha and x alpha is 0 for almost every alpha. This almost every alpha means all but a finitely many, for all but a finitely many alpha, x alpha is 0. Okay, so what we get from this sum is that if you take radical of I plus j, then that is the same as taking radical of radical I plus radical j. So radical I is contained in I, radical j is contained in j. I is contained in radical I and j is contained in radical of j. And then you can see that the sum of them is contained in the sum of these radicals. And this sum is again contained in the radical of radical I plus radical j. So one side is done in that way. And for the other side, if you take some x from radical of radical I plus radical j, then your x power some m is of the form y plus z, where y is in radical I, j is in radical j. So z y power some l and z power some k is in I and j respectively. And then you do the similar trick of binomial kind of expansion. So you take the power, let's say L plus K or something like that. That will show you that some power of X, you take Y plus Z and raise it to the power that L or whatever, L plus K or something like that. Then it will just break into terms of I and terms of J. And thus this X power L plus K will be inside I plus J. Thus it belongs to radical of I plus J. So this is also done. Okay. And again, by the virtue of this statement, sixth statement and this one for prime ideals, what we get is that if you take radical of prime power n, some prime ideal raised to the power n, then that is the same thing. Okay. Also, the most important characterization that is coming in view of this observation, that your radical of I is actually the intersection of prime ideals of A such that I is contained in P. That has to be, because nil radical of A mod I is the intersection of prime ideals of A mod I, and that is when you take the pre-image, that turns out to be the intersection of prime ideals of A which contains I. Okay, so this is what I wanted to at least say as an introductory remark about radicals. Okay. So having done some amount of theory for radicals, so we have talked about Jacobson radical, nil radical, and in general radical of an ideal, connecting them to nil radical in general. Okay, so now we are in a position to talk more about this intersection of ideals, etc. Okay. So the next result, what I am going to prove, is called the Chinese remainder theorem. Again, that has some applications in general in ring theory. That's a very important theorem in view of number theory, ring theory, etc. But what I feel is that maybe I will stop this lecture with the discussion of radicals, etc. for now. And in the next lecture, we will talk about two fundamental theorems, which I have mentioned earlier. That is the Chinese remainder theorem, and another is the prime avoidance lemma. So thank you.